In this short video we're going to look at how to derive the error in a NewtonCotes integration formula. The way in which we'll do this is to consider the case of a linear polynomial approximation to f of x. So if this blue dashed curve here is our exact function f, we're going to look at what happens when we fit a linear approximation p of x, that's the green line in the figure. Now, without loss of generality, and that's what WLOG stands for, we're going to let the x range of our analysis go from 0 to h. And there's no problems whatsoever in doing that. It's just a simple coordinate transformation to shift to some other range, and it's much easier to do it this way. So the error between our linear polynomial approximation p of x and our exact function f of x is that shaded pink region. And that's going to be the error when we use p of x and integrate that instead of using the exact function. And we're going to define a functional form for our error. We're going to call it epsilon. It's a function of x. It changes over the range from 0 to h. And it's equal to f of x, the exact solution, minus p of x, our polynomial approximation. And that varies as we go from 0 to x. And quite clearly at the endpoints, epsilon of x is equal to 0. So e of x is equal to 0, and x is equal to 0, and x is equal to h. So we're only going to consider the case of a linear polynomial approximation here. You can do higher orders. The analysis becomes far more complex, and it's not really very illustrative. So we're just going to do the simplest case. So our aim in the next 4 or 5 slides is to define our error, epsilon of x, in terms of the exact function, f of x, and derivatives of the exact function, even though we don't actually know what f of x and its derivatives are. So we have two known values of f of x at the endpoints, that's f of 0 and f of h. Using either of these two values, we can estimate the value of f of x using a Taylor series expansion, either about 0 or about h. Alternatively, and this might seem like a strange way of doing things, we can also estimate the value at f of 0, or the value at f of h, based on a Taylor series expansion about x. And in actual fact, that's what we're going to do. Even though it seems like an odd thing to do, it'll make sense when we finally get to the end result. In doing this, then, we can determine a function for the error. Okay, so let's look at the first thing we need to do. What we want to do is to approximate f of 0 as a Taylor series expansion about the point x. And remember, the point x lies somewhere in the region from 0 to h. So x is some point in the middle here. So we write equation A, f of 0 is equal to f of x minus x times f dashed of x plus x squared on 2 f double dashed of x minus x cubed on 3 factorial times the third derivative, etc. That's just basic Taylor series stuff. You really need to know that by heart. Also, and this is completely separate to the previous equation, we note that the straight line p of x can be written as p of x is equal to p of 0 plus x times dp dx, evaluated at the point x. In other words, p of x is equal to p of 0 plus x times p dashed of x, and p dashed of x is just the slope of the straight line. Another way of writing that then is p of 0 equals px minus x p dashed of x. In actual fact, it's the same way of writing it. I've just written it down twice. So we have two expressions, a and b. If we subtract b from a, we're going to subtract p0 from f0, and we note that p0 and f of 0 equals the same, because that's the polynomial passes through f of 0. We also note that f of x minus p of x is actually equal to our definition of the error, epsilon of x. So if we go through and do that, we end up with equation C, which says that 0 is equal to our error, epsilon of x, minus x times f dashed of x minus p dashed of x plus some higher order terms. We're going to ignore most of those higher order terms. We're only going to keep this one in the subsequent analysis. So equation C we're going to come back to in a few slides. Let's look at the other way of looking at this. Let's approximate f of h as a Taylor series expansion about x. This then gives us equation D. So f of h is equal to f of x plus h minus x times f dashed of x plus h minus x squared times f double dash plus these higher order terms. And again, we note that the polynomial, our straight line, p of h can also be written as p of h is equal to p of x plus h minus x times p dashed of x. And again, remember, p dashed of x is just the slope of the straight line. Very easy to convince yourself that this is true. Again, we're going to subtract equation E from equation D. We note that f of h and p of h are equal to each other, so that subtraction is going to be 0. We notice again that our error is just equal to f of x minus p of x, so that is going to be the error term. And if we do the subtraction, we see that 0 is equal to epsilon of x plus h minus x times f dashed of x minus p dashed of x plus a second order term plus higher order terms that we're going to neglect. So equation F is the other equation that we need to use. So just writing equation C and equation F again, what we've got now is we've got two different expressions for our error, one in equation C and one in equation F. So let's divide equation C by x. Divide that by x, that will cancel out. All of that will be divided by x. That gives us this equation there. And let's divide equation F by h minus x. That will disappear, and all of this will be divided by h minus x. That will end up with the following equation. C1 is 0 equals epsilon x on x minus this term plus higher order terms. And F1 gives 0 equals epsilon of x divided by h minus x, again, plus a term that's identical, plus some higher order error terms. Let's get rid of this first derivative term because we actually have no idea what f dashed of x is equal to. We can get rid of it by just adding C1 and F1 together, because we notice that this term here appears with the opposite sign in each expression. If we add these two terms together, we get the top line here. We've got a sum of these two error terms plus some second derivative terms. I'm not going to go through the details of deriving this, but it's pretty easy to show that the first term involving the error is equal to h divided by x times h minus x times the error term plus h on 2 times the second derivative of x plus some higher order terms. And that, of course, as we've already seen, is equal to 0. So solving this for epsilon of x, we just need to divide by that term there, gives us an expression for the error, which is what we're trying to find, that the error as a function of x is equal to x times x minus h, that's that term at the bottom there, divided by 2 factorial times f double dashed at x. And remember, this h term has cancelled out here when we've multiplied by this here, plus then some higher order terms that we're going to ignore. So, assuming that the leading order error term is the largest, and that's usually a pretty good thing to do, we have shown that the error as a function of x, when we fit a straight line to any function, is approximately equal to x times x minus h divided by 2 factorial times the second derivative of our function at the point x. Of course, if we don't know what the function f is, we don't know what its second derivative is either. So it's a little bit difficult to use this directly to estimate the error. However, it's still extremely useful, as we'll see in a minute. Now, just as an aside, we can apply a similar technique to the nth order Lagrange polynomial approximation. The mathematics rapidly becomes extremely difficult, and that's one of the reasons I have no intention of trying to show it to you in this class. It doesn't really give you very much illumination as to what's going on. The linear case really contains all of the essence of the approach. In general, however, for a Lagrange polynomial of order n, the leading order error term can be written like this. So it's equal to the n plus 1th derivative multiplied by a product of terms. And this will be a term that looks like x to the n, or x to the n plus 1 in actual fact, but be proportional to the n plus 1th derivative. Okay, so going back to the trapezoidal rule, we found that the error in the linear Lagrange polynomial, which is what we use in the trapezoidal rule, was given by this expression here. The trapezoidal rule uses this linear polynomial, the linear Lagrange polynomial, as an approximation to our function. Thus, an error estimate in the trapezoidal rule can be obtained by integrating this error function here over one interval. So the error then is going to be equal to the integral of epsilon of x from 0 to h, that's our interval, and we just substitute epsilon of x by that into our integral there. Now, to perform this integration, we're going to make a further assumption that across this interval, our second derivative is approximately constant. Now, this is a reasonable approximation, provided h is small. Now, if h is really big, then it becomes less good. So this is only an approximate analysis. But it's not too bad when h is small. If we actually undertake this integral here, we bring out the f double dash because we're saying it's approximately constant. The integral of x squared minus xh is just equal to x cubed on 3 minus x squared h on 2, and if we calculate that between the limits of 0 and h, it's very easy to show that this error term is like minus 1/12 h cubed f double dashed of x, where this is some kind of approximate integral, approximate estimate. So this is what we actually stated a number of videos ago that the error in the trapezoidal rule was equal to. So for a single interval, the error scales like this, and we've introduced this concept of a psi. In actual fact, using the mean value theorem, you can prove that there is some psi which lies in the region of 0 to h, where the error is exactly equal to negative 1/12 f double dashed times h cubed. We don't know what the value of psi is, and we don't ever need to know it, but you can actually prove that this is an exact equality for some point inside this interval. For a single interval, we've got the error given by that, but really, when we're using the composite trapezoidal rule, we're summing up over multiple intervals, multiple segments. And so for multiple segments, clearly what we're going to have to do is we're going to have to sum all of the individual errors. And so if we do that, we end up with an expression. The total error for the composite trapezoidal rule is negative 1/12 times the sum over each of the segments of f double dashed of some value of psi within each segment multiplied by h cubed, where h is the segment width. Now, what we're going to do here is we're going to pull the h cubed out of the sum because it's a constant. We're also going to pull out an n, but we're going to divide by n as well. So effectively we're multiplying by n and dividing by n, so we're not doing anything to the value of this particular function. And we see that, well, first of all, that b minus a is equal to the number of segments times the segment width. So we can calculate that n is equal to b minus a divided by h. We actually want to get rid of this n that we've got in the expression here. So we replace that by b minus a divided by h. Therefore, the h cubed becomes h squared times b minus a. And we're left then with this term here at the end to try and do something with. But what we're doing here is we're summing up over each of the intervals the second derivative at some point in the interval, and we're dividing it by n. So that term there really is an approximation to the average second derivative over the interval a to b. Therefore, total error in the composite Simpson's rule is equal to the width of our total domain, b minus a, times h squared, the individual interval width squared, on 12, times some estimate of the average second derivative. Now, usually when we're integrating, the b and the a are fixed. They don't change. We don't really have any information about what the second derivative is, and certainly not what the average second derivative is, but in actual fact we don't usually care what that is. The most important thing to come out of this analysis is that the error scales like h squared. In other words, if we make h half the size, the error goes down by 1/4. That's the most important thing to come out of this particular analysis, is this scaling argument down there. So that's why, that's what we've done now, is to actually demonstrate that even though the error in a single interval scales like h cubed, the error over multiple segments scales like h squared. Now, if we look at the error in higher order NewtonCotes formula, for example, Simpson's 1/3 or 3/8 or even higher order ones, we can do a similar analysis. Now, because the leading order error term in the nth order Lagrange polynomial looks like this, we've already seen this before, the error in the NewtonCotes formula can be found by integrating this formula here over the interval of the method. So, for example, for Simpson's 1/3 rule, we would need to integrate this expression over 2 segments. For Simpson's 3/8, we'd need to integrate it over 3 segments. It turns out that for even n, so 2, 4, 6, and 8, the leading term above integrates to 0. And in actual fact, we need to include the next term in this expansion. So there is another term down here, which scales like f to the n plus 2. That'll be n plus 2 factorial. And this will be a pi term that goes from I equals 0 to n plus 1. Haven't actually shown that here. The fact that the leading term integrates to 0 for even n leads to the error in Simpson's 1/3 rule scaling like h to the 5th. And we get a higher accuracy than we would expect to with Simpson's 1/3 rule.